Okay, awesome. So for you guys who are taking Calculus 1 first time and you're having to deal with limits, asymptote. So I'm going to break down today something very simple. And it's essentially there's a definition of asymptote that is related to limits. So it's easy when you're in algebra, right? You would consider an asymptote to essentially be wherever you have some sort of infinite behavior. So if you had a function that suddenly kind of shot up like that, and then maybe continued like something like that. So we have to find ways to talk about curves that don't behave very pretty. You know, they go into these things. So what I'm gonna do, instead of just giving like a typical talk about asymptotes and just giving the stock definition, there's a very easy way to basically come up with the definition that you'd find in your AP calculus course or whatever. So what we're going to do is we're going to just start with a very, very fundamental curve, the inverse function. So y equals 1 over x. And if you are a calculus 1 student and you cannot draw the 1 over x, the inverse function, just on the spot, get there, because this is one of the most important curves in the study of calculus 1, in my opinion. And the reason why is you can use this for so many different things, but specifically, this is a great way that you can kind of rederive the definitions of asymptotes. So the first thing, obviously, is that there's a big, obvious asymptote right down the middle here. And this is a vertical asymptote. At x is 0, and then this is great because of the symmetry, you get another asymptote along y equals 0. But instead of getting right to the asymptotes, we're instead going to just explore, do a few different limits, and then you'll actually find there's this really wonderful way to talk about an asymptote. So with limits, you can approach a various location along the horizontal axis, and then you talk about how does the function behave as we approach various parts along the curve. So if we were to do so for all these examples, we're just using y equals 1 over x. So if we were to do a limit as x approaches 0 from the right, and I don't know, oh, the glare is really bad on the whiteboard. I'm not gonna do it there. I'll do it right here. So the limit as x approaches 0 from the right of 1 over x. Well, when you look at the curve, it's pretty straightforward, right? So here's positive x, and we're moving towards x equals 0. And as we do that, the curve is just going, and it's rocketing straight up to positive infinity. So we're going to say that our curve behaves, so this equal sign is not a statement of like computational equivalence, it's a statement of behavior, is behaving towards positive infinity. Okay, so the limit as x approaches 0 on 1 over x is infinite behavior, positive infinite behavior. And if we want to talk about the limit as x approaches negative 0 from the left this time of 1 over x, well, you get a similar result, right? But instead of coming at x equals 0 from the right in, we're coming from the left in. And since we're on this bottom piece, we instead shoot all the way down to negative infinity. So this is behaving and it's going to trend down toward minus infinity. Okay, so we have two limits, and whenever there's an infinity or the concept of infinity involved in a limit, we call it an infinite limit. So infinite limits is a special type of limit, and they're honestly the most useful type when we're talking about calculus 1. And so what do we notice about these two limits? Okay, so x was approached from the right. We got an infinitely behaving result, and then we approached 0 from the left, and we also got an infinite behavior. And so this can lead us to the conclusion. All right, so we could say, all right, if our limits on both sides trended in infinite behavior, as we approached both sides of a particular point, That is a very specific kind of behavior, and that is how we define the asymptote. The asymptote is basically, so if we have, if we are able to show that the limit as x approaches some value a, doesn't matter, because once again, not every single function is just the basic 1 over x, right? So as x approaches some a value along the horizontal axis from the right, so some function equal, if this is equal to plus or minus infinity, it doesn't matter, right? As we can see, you can approach a positive infinity, like as we did over here, you went up to positive infinity. You could approach a negative infinity. The point is, you're doing something infinite in either direction. So if that happens, or it's important to note, not only from approaching from the right, but we could approach a from the left. And if this also equals plus or minus infinity, if we can show that either of these statements is true, then there is a vertical asymptote at x equals, and then that a value, right? And that x equals a. So in this case, we were approaching x equals 0. So a is equal to 0 in this case. And we approached it from the right, we got positive infinity. So right there, we could have concluded then there is a vertical asymptote at x equals 0, because we tried to approach it and we got some infinite behavior. And then in this specific case, there's due to the symmetry with 1 over x, it happens in both sides. So if you approach the left and the right, that's going to happen for you. Now, this thought process, this idea, we can take a limit, and then based off of the way it behaves, we can it makes an immediate conclusion about its asymptotes. This is what we do for vertical asymptotes. We let x approach a fixed constant value, and then we take a look and see if it behaves infinitely. The only difference between, so this is vertical, right? So this is for vertical, not horizontal asymptotes. The vertical asymptotes deal with x approaching a constant value and then seeing if that gives you an infinite behavior. And the difference between the only difference between the vertical and the horizontal asymptote is going to be simply what we choose to approach and then what happens. And so you literally just flip-flop. So here, I'm going to go through this. X approaching infinity, so some infinite, and if we stick the infinite idea down here where x is approaching, and then we instead stick the constant out here, that's where we make a conclusion about horizontal asymptotes. So keep note of that pattern. I'm going to erase this part and then go through the horizontal asymptotes. But this pattern right here, just really take note of how kind of beautiful this is, because we take all of these concepts and we also use it as strategies to break down other limits where you might not think, oh, I could use that kind of an idea to reduce this limit over here, which is somewhat unrelated. So let me clear some space. So with the vertical asymptotes, we were talking about letting x approach a constant value. In this case, we were letting it approach a constant value of x equals 0 and seeing what happened. Now what we're going to do is we're going to let x approach, like basically trend toward infinity. We're going to talk about infinite limits. So the limit as x approaches infinity now. So that's what I meant. Now we're sticking the infinity down here. So x is approaching infinity, 1 over x. What is this going to trend toward? What is the behavior here? Well, with 1 over x, this is kind of straightforward, right? It's pretty clear and very soon that this asymptote comes down and it's basically behaving like 0. So as x continues to just blow up and toward infinity, it's going to the right and right and right. This curve is just going to flatten out. It's going to look like 0. So we know that this behaves like 0. The limit as x approaches positive infinity is 0. Okay, that's pretty straightforward. We can do that we can approach infinity in the positive direction and in the negative direction. So what if we took the limit as x approached negative infinity of 1 over x, right? That looks like a t. There you go. What does this equal, right? So if we decide to go instead blow up in just unboundingly large, and instead we try to go unboundingly small or negative, we're still going to come up with the same thing. With this specific function, 1 over x, we're still going to essentially approach 0. So if we go this direction, we still approach 0. The exact values here isn't what's important. It's this concept that we took the variable x. We asked the question, what happens as we blow it up in some unbounded direction, either positive infinity or negative infinity. But instead of the limit also blowing up to infinity, it actually just came down and it converged to some constant, right? That's important. And notice that that's precisely where we have our horizontal asymptote. So we can make a conclusion. If we can show that the limit as x approaches either positive or negative infinity, it's a little bit smaller, but you can see it. But as the limit as x approaches positive or negative infinity of your function is equal to some constant value b. So b is going to be like a constant, kind of like how 0 was a constant here. So if this is able to approach a constant value b, and then we can come to the conclusion, then there is a horizontal asymptote at y equals b. So that equation of the line y equals b, that constant value. And in this case, it's true, right? Here, x approached infinity or approached negative infinity of the function, and we got a constant b equals 0, where you got a constant value. And so therefore, we made the conclusion directly. All right. Well, then that means there must be a horizontal asymptote at y equals b, right? Y equals 0. And that's exactly what we have with the function 1 over x. And so you might be wondering, okay, that's great. And it is. These are the two definitions. So vertical asymptote definition, if the limit as x approached 0, or not 0, sorry, a constant value, any constant value, x approaches some a, and then you get some infinite behavior, then you have a vertical asymptote at the line x equals a. And I'm going to stress that it's a line. Asymptotes are not scalars. They're not just single values. So if you're ever asked to name an asymptote as a mathematical object it's a line, it's an equation. So there should be an x or y equals something, right? It's got to equal something. You have to have a line. So the horizontal asymptote would not just be 0. If you just wrote down 0 and said that's the horizontal asymptote, that would be wrong. Because 0 is not a line. It has to be y equals 0, right? It's ambiguous if you just write down a number and say that it's an asymptote, because it has no meaning. An asymptote is an equation. It's an equation of a line because an asymptote's a line. So keep that in mind. That's one of those kind of bonehead mistakes that can often be made for top 1 students, is that they do all of the math correctly. And then at the very end, when they're asked to name the asymptote, they just put the constant value that they found instead of actually the equation of the asymptote. So don't be that person. But we can take these principles and now extend it to things that might not necessarily be directly related to the asymptote. For example, there's really cool consequences in that, especially with this particular graph, is that you can show that when you take limits of something, if you have some constant value over something that approaches 0, well, it's going to behave infinitely. And if you can also show that if you have some constant value over something that's approaching infinity, then it's going to trend towards 0. So that's another really, really powerful conclusion that you can derive from just looking at y equals 1 over x. So really, in my opinion, which isn't, I don't know, that weighty, I guess. But limit should really just be centered around this beautiful function. You can learn so much and gain so much intuition from just taking a look at the way this thing behaves and then relating it to concepts as you go along. And so if you have like a practice problem, for example, and it's asking you to solve, hey, find the vertical asymptote and find the horizontal asymptote of this function if they exist, okay? So how can we practically apply this knowledge? There's a trick for vertical asymptotes. And remember, it's the idea that the function is going to behave infinitely at a certain point, specifically when that function is going to be undefined for the very specific reason of that it would be dividing by 0. Okay, so you notice that with y equals 1 over x, we could really talk about just a general function y equals k over x, where k is a constant value. Okay, k is some constant, and you have an x. And whenever x approaches 0 in this case, so whenever we have the limit as x approaches 0 of k over x, this is going to trend towards positive infinity. Okay, and likewise, so this comes from our understanding of the vertical asymptotes. So if we have something that blows up to infinity, now we also can talk about the opposite is true. Like, so if we have the limit as x, instead of approaching 0, we approach affinity of k over x, we actually that goes down to 0. So there's this we call it, it's not really a true inverse relationship, but it's really, really kind of interesting how those two numbers kind of flip-flop. So the 0 and the infinity here, then the infinity and the 0 here. And so oftentimes what we can do, that leads us to be able to show a rule so that if we have some limit, so let me use this space right here. If we have some limit, x approaching 0 of some function, say like f of x. And if we know that this is going to behave infinitely, what we can do is this allows us to basically flip things around and say that the limit as x approaches infinity is actually just the same as taking this 1 over f of x. See? And so sometimes that can be really, really useful to substitute the reciprocal into a problem and take its limit. So for example, if you had to take the limit, let's see. Now as x approached infinity, so the limit as x approaches infinity of sine of 1 over x, right? So the idea here is that this is reciprocal. So you could substitute a reciprocal and note that you're dealing with the same behavior. There's two different ways to think about this, right? This infinitely going behavior over this constant over a variable that's going to trend towards 0. And so you can flip things around and you can say, well, x approaching 0 of sine, take the reciprocal of 1 over x. The reciprocal of 1 over x is just x. So now this limit looks a lot prettier and conceptually can be a lot easier to solve because now you know you can just substitute that 0 in for x and you have the sine of 0, which is equal to 0, right? So that is why, that's one of the many uses that's useful to know that you can kind of take that reciprocal whenever you kind of flip those things around. So that's one consequence. Another consequence that's very beneficial is that if you've ever heard the shortcut, so a lot of times what teachers will do in a math class, they'll say, okay, well, if you ever have a ratio of two things, so if you have some polynomial f and some polynomial g, in order to find its vertical asymptote, you just set g equal to 0 and then figure out when that's equal to 0. The reason why that works is because of all that work we just did. We just showed, because ultimately this top function is just going to be some constant value divided by something that's approaching 0. And you cannot divide by 0. And that motivates everything that we talked about. You get that infinite behavior. What does infinite behavior imply? It implies a vertical asymptote. So in case you're wondering why that rule works, it's because of that limit. It's about talking about the infinite behavior in the limits. And so if you had to find basically the vertical asymptotes of a ratio like this, you get something in the top, something in the bottom, set the bottom equal to 0. And that's kind of like the fast way. And it's a way to take advantage of that intuition to just get straight to vertical asymptotes. Now, the horizontal asymptotes are going to be a little bit different, right? To find the horizontal asymptote, you're going to ask yourself the question instead, I'm going to take the limit of this thing and push x to be an infinite value, right? So in this, you could try positive infinity and double check for right hand, or you could check x as it approaches the opposite direction. Right? You want to check both ways because it is possible for there to be a horizontal asymptote that it only extends into one side, only one direction, the positive or the negative direction. So it's always really important to check both sides to make sure that you don't end up getting some constant value, because the moment you get a constant value, you know you've just identified a horizontal asymptote, y equals b, whatever that constant value was. And this also, see, that's the thing with the limits, it's all interrelated. Once you get the central concept kind of just the behavior of things, it leads into the rest of the topics you'll cover. End behavior is a big topic, I think, in AB. Not so much in BC because BC has to push through like extra units that AB doesn't really have. But in AB especially, make sure you understand what end behaviors are. And this, think about end behavior in terms of asymptotes and this behavior kind of stuff. Because like I said, the reason we have to check x goes positive infinity and x is negative infinity is because you might have a different behavior depending on which direction you're going. And that's what we call the end behavior function. How the name of the function of how it behaves depending on the direction that you're going. Right for positive infinity, left end behavior for negative infinity. So that is kind of the very, very brief crash course of limits surrounding infinite related things, which includes, and that's why asymptotes are just kind of categorized under, in my opinion, just the study of limits that deal with infinity as a concept. And then behavior as you move through the units, and eventually derivatives, a good definition, the limit definition of a derivative. So that's all I have for today. Hopefully that was useful to you. And for those who couldn't come, I'm just going to record, it's being recorded right now, so I'll upload that. But anyways, hopefully that was useful. Thanks so much.